People are gonna want to hear this one, I think. So I'll say it one more time for the recording. We're really excited to be welcoming Ben Criger today. He's joining us from the UK. He received his PhD in theoretical physics from the University of Waterloo in 2014. Since then, he's been researching fault-tolerant quantum computing in Germany, the Netherlands, and the UK. And he's also had a little stint working in non-fault tolerant quantum computing in Singapore. So very excited to hear about that. And he says that in his now dwindling free time, he used to build rockets and promote one-way travel to Mars. And now he mostly thinks about work while desperately attempting to lose weight, as most of us do during COVID. So Ben, please take it away. We're really excited to hear all about what you do.
All right, now the moment of truth where we figure out if Science Boy can figure out how to share his screen. Aha, the host has disabled participant screen sharing. If only the host would enable participant screen sharing, then
all right,
we would be on track.
That is on us.
Zoom is a fantastic piece of software. My company makes software. We employ programmers, and I am constantly, I am like a never-ending source of spleen fluid, right? I just vent all over these guys all day. One of them worked on an NHS app. So whenever the NHS app, so before he came here, he was working for the NHS on an app. Whenever that thing goes down, I'm like waving it in his face. Sam, hello, where's the app? But yeah, so let's see whether Zoom.
You should be able to share it now. I made you a co-host.
All right. Aha, excellent. Okay, now.
Perfect.
I should also apologize for the bait and switch. Title of today's talk was supposed to be, it is rocket science, but I ran into this question of whether it actually is rocket science. There's a lot of really important stuff out there that has nothing to do with rockets, although it's still science. So that's what we're going to talk about today because I'm in charge. Although now that we're being recorded, I can't say anything too lascivious or weird, so I'm going to have to stay very mainstream. But, you know, with that small, warning for what would otherwise be an extremely exotic presentation out of the way, we can begin. So we're going to talk about who I am, even though, you know, the audience, maybe you know me better than I know me. So, I was going to say, oh yeah, I'm from Hamilton. I had my bar mitzvah at Anshe Shalom, but many people in the audience today don't need that explained to them because they were there. So maybe we'll not take too long with the intro. Then we're going to get on to what the main topic is that we should talk about. What we're going to do once we, have concluded talking about that thing, and then I'll wrap up in the sort of typical intellectually lazy fashion that people say, oh, you're supposed to tell them what you're going to tell them, then tell them what you just told them. I will tell you what I just told you at the end. All right, so who am I? That's me. I'm a schlub in his mid-30s with a PhD, as Misha mentioned. I've been working all over the world. And now I think I'm so hot, right? I've been described by close friends and associates as a STEM lord. I don't know if people know what a STEM lord is. It's this type of guy who thinks that like engineering, math, technology, and science are supreme, and people from the humanities are like chumps, right? And I've been educated to the degree that I occasionally reflexively lurch into that stance at times, especially when somebody from like a really high up university, but a different department like comparative literature or something is trying to get at me about what's the good university. And I'm really into, and I'll admit it, this is like a huge blind spot for me, modernism. The idea that we can sort of improve the world through technology, better living through chemistry, and a lot of stuff that, people might have espoused in the 50s or whatever in the pages of Scientific American, that, has since been, really fiercely critiqued by generations of postmodern scholars, talking about how all those people were biased, etc. And I'm also biased, but at least I'm honest about it. Oh yeah, and I wanted to mention that I moved from Singapore to the UK. The photo is from Singapore, and you'll notice that in Singapore the shirts are better, but the haircuts are worse. Now, despite being a modernist with this nice haircut, I still like to think that I'm a compassionate guy, even though, I spend most of my time thinking about technical topics rather than individual people and their needs, emotional or otherwise.
Ben, could I interrupt you really quickly? I
Sure.
heard some people are having some trouble hearing you. I'm not sure if you can speak up or make sure the mic is closer to your mouth. I'm okay, but I think it's better to have it a little bit louder if possible.
How's that?
Oh, amazing. I think that's
Okay. All right. And you're not getting like background noise or anything?
nope.
Okay, fantastic.
Perfect. Thank you.
All right. So I won't go over all the intro stuff again. You know me. So today's big issue that we're going to talk about is as a young-ish Jewish person, there are very few concepts from the Torah that resonate with me. I think this is, ubiquitous across modern Judaism. But Tikkun Olam has got to be like the one idea that has stood the test of time. It's the idea that, the world is in need of repair. And so your duty as a Jew is to do that repair. For a long time, I have wanted to tikkun this olam, that's Mars, and it's in desperate need of repair. Its atmosphere is unbreathable, it's extremely cold, but it's got all of the crucial ingredients that are needed for life to flourish. Carbon, oxygen, hydrogen, nitrogen. And, if those atoms and molecules are arranged in the right way, we can have a prosperous and beautiful civilization. But, it's sort of like being in the backseat of the car saying, can we stop for food? And your parents would turn around and say, we've got plenty of food at home. There's enough olam to tikkun back here at home. And we've got one specific problem that I'm going to talk about. Now, okay, Tikkun Olam is a very broad idea. There are a large number of problems you could try to fix: war, poverty, oppression. But these things are sort of purely political. They're matters of law and systems of human decision-making. And so there's very little room for a scientist to help out. It's a matter of how do you force a powerful institution to do the ethical thing? And you can't do that by with algebra, right? It's not the right tool for the job. So today, we're going to take a look at the Earth's atmosphere, which has the wrong chemical composition. It's got 420 parts per million of carbon dioxide, and we wish it would have something more like 350. Although maybe 350 is too much. These specific numbers are not meant to be as useful as the techniques that I'm going to show you today, and many people are probably already familiar with, for figuring out what these numbers mean and what to do about them. There are a couple different approaches. I mean, it's not as if I'm the first person ever to raise this issue. A lot of people already know about it, and there are already tons of solutions on the table. Of course, there are more than two camps, but I'm going to divide people broadly into two camps. There's Bill Gates on the right, who, I mean, it was back in 2015, but let's suppose that he's still behind this, is into what's called solar geoengineering, where, in response to global warming, you spray reflective particles into the upper atmosphere where they hang out for a long time and reflect sunlight in order to reduce the amount of energy that comes into the earth and cool the place down. And this has been roundly criticized by people like Naomi Klein on the left, who lambasts the idea of a techno fix and proposes political solutions instead. But in the spirit of being as critical as possible, I'll say that both of these people are wrong, right? Bill Gates should be more amenable to political solutions because it's the current political arrangement that's made him, a gazillionaire. Microsoft Windows isn't that valuable. The contracts and the legal restrictions on people copying software, which otherwise would be a cost-free way to spread it around, right? That's what's made him rich. And Naomi should be more into techno fixes because she's got a techno fix for her bad eyesight, right? She's wearing a pair of glasses, as many people do. Of course, if there was no such thing as glasses, we could come up with political solutions to poor eyesight, right? Recognize it as a disability, make sure that there's facilities for text to be made bigger and anywhere, where people have to read it, public programs to transport people with poor eyesight around so that they don't have to drive themselves, which would be quite dangerous. But it turns out to be cheaper and more convenient and more liberatory for everyone if we just figure out, that there are lenses in the eye, and then if you put lenses on top of lenses, you can make effectively new lenses and adjust people's eyesight to be what they want it to be, and then give them the power to do so. Right. So the idea here is that, there's an intersection between political solutions to problems and what we would otherwise denigrate as a techno fix, and that's science, right? The idea of having a sort of secular external assessment of how big a problem is, what its nature is, what it's made of, and you can then decide whether it's possible to address it using technology or to spread costs politically. Now, when people talk about the parts per million of carbon dioxide in the atmosphere, this number is almost impossible to understand because they never say how big the atmosphere is. And so, a part per million remains a sort of abstract, ungraspable concept. So let's put this number in context, and I'm gonna steal a technique from David Mackay, who wrote this book, Sustainable Energy Without the Hot Air, which is one that I really respect and I recommend to everybody. And he went into a lot of detail about how much land is taken up by renewable energy solutions, how much concrete you have to pour, and how many watts are created. And importantly, didn't propose an individual plan for powering. Well, the country does case studies on the UK, or the book does case studies on the UK, I should have said. So he didn't propose one concrete way to power the UK, but rather provided the sort of the arithmetic and a few facts and figures that people need to determine what their own preferences are in terms of sustainable energy. And I'd like to give that a shot, although this isn't going to be as detailed as that book, which you should go read. So let's begin by saying that the mass of Earth's atmosphere is 5.148 times 10 to the 18th power kilograms. But a lot of people might not be familiar with, X times 10 to the Y kilograms or what have you. So we're going to go just into a little bit of review about what X times 10 to the Y means. So this is called scientific notation. It's a way to economically write down really big numbers. So 100, for example, is 10 to the second power, right? It's 10 times itself twice. 1,000 is 10 times itself 3 times, which is 10 to the third power, or 10 cubed, right? And you can imagine that if I tried to write down 10 to the 18th power, it'd be like a 1 followed by 18 zeros, and it would take up the whole width of the slide and be really inconvenient. So this is a sort of shorthand for making sure I don't need to write down a bunch of digits. And here's a final example, right? These are the kinds of numbers that we'll be dealing with, which is some constant, well, not a constant, but some number that's less than 10 and greater than 1 being multiplied by 10 to the somethingth power, right? So 36,900, for example, is 3.69 times 10 to the 4. So in order to figure out how big the problem is, right, how much carbon dioxide do we have to remove from the atmosphere, we're going to take the difference between 420 and 350. That's the number of parts per million we would have to remove, right? That's 70. Divide that by 10 to the 6, right? 10 to the 6 is 1 million, and this is parts per million. That's where that dividing by 10 to the 6 comes from. And then you just multiply by the mass of the atmosphere to get 3.6-ish times 10 to the 14 kilograms. But this is another sort of ungraspably large number. Nobody's ever seen 10 to the 14th power of anything, let alone kilograms. And we don't know how much carbon dioxide is in a kilogram anyway. So we need to sort of scale the number again and get it down to a size that we can efficiently think about ourselves. And this goes for me as well, right? Having a PhD doesn't give you superpowers, and it's really tough to think about, what is that, 100 trillion of something, regardless of, how experienced you are with math. In order to comprehend this amount of carbon dioxide, I'd like to try and divide it by the population of the Earth, which is 7.753 billion people. A billion is 10 to the 9. And what we're going to end up with is 4.65 times 10 to the 4 kilograms per person, which is 46.5 metric tons per person. So you can imagine something that weighs 40 metric tons or so. 1 metric ton is about 1 cubic meter of water. So if you have a pool, it probably contains about 46 metric tons of water. If it's a small pool, it might be half that. A big pool might be twice that. But that's about the mass that we're talking about. Of course, carbon dioxide at room temperature is a gas, and so you wouldn't be able to fit all of that average person's worth of carbon dioxide in a pool. You'd have to use a cube that's about 29 meters on a side. But this is still getting into the range of sizes that we can efficiently think about, and the problem gets even easier to think about and maybe even to solve if we talk about the carbon instead. After all, it's okay to have all of that carbon dioxide, transformed into carbon and oxygen separated, and then just vent the oxygen into the atmosphere, right? The atmosphere is already 21% oxygen. Having another few parts per million or 100 parts per million isn't going to make much of a difference. And the carbon would actually be about 1.77 meters on a side if it were crushed into a cube with the maximum density. And 1.77 meters is just a little bit taller than me. So that is a size of cube that we can definitely understand. And now that we've understood the size of the cube, we are more able to think about and discuss solutions to this problem, which I hope resonates with you as well. And the cube seems a lot less abstract than the 420 parts per million. So let's imagine that I was to try to buy my way out of this problem right now. Now, it might seem like I'm promoting individual solutions to climate change, where you just take care of your bit and then rely on everybody else to spontaneously decide to take care of their bit. I actually don't think that would work. I'm just getting a sense for how difficult the thing is that the average person would have to do. I actually hope that it would be easier if we use teamwork and division of labor to sort of break the problem up, so that we don't all have to, for example, go on Alibaba and price out a bunch of charcoal from Vietnam. Vietnamese charcoal costs about 44 cents for 10 kilos, as long as you order at least 19 bags. 46 metric tons is a lot more than 19 bags, but it's only about $2,000. So something like this, if it can be scaled up, which, there's a big asterisk on that, but prices as they are today are not prohibitive, right, in terms of obtaining the carbon and sticking it somewhere where it won't turn back into carbon dioxide, maybe under some nice damp soil somewhere so that it doesn't burn. And, the remaining problems on top of this are mostly social and political, right? If I was to buy these big bags of charcoal and then tell the people who make it, just bury it somewhere, don't ship it to me, odds are they would just go sell it to someone else. And they'd be, more or less right to do so, because 10 kilos of charcoal over in North America fetches a much higher price. So there are lots of other middlemen in this operation that are getting paid a lot more than the people actually making the charcoal. So if they get one over on old me, right, then I can't really fault them. At the same time, though, let's imagine that I was really serious about this and that I wanted to make sure that I could keep that carbon in the ground. So I would try to char it myself, right? Grow a bunch of wood and then stick it in a closed canister, heat the canister up, so that, all of the water and other volatile compounds come off. Maybe they get burned, and what I'm left with is carbon that came out of the atmosphere into some wood and then into a nice stable form so that I can stick in the ground. Here's a chart from A.J. Nath et al. In a journal called Global Ecology and Conservation, where they consider doing this with bamboo. Now let's see, if you can see my cursor, then I'd like to draw your attention to this column in the middle that says biomass carbon sequestration rate, and it's in megagrams per hectare per year. A megagram is a very fancy way of saying a metric ton, but it says here that you can get an amount of carbon if you're a decent farmer, although you don't have to be that good because bamboo grows like a weed, it's technically grass, and you can even grow it on marginal land that's not used for food. So you can get anywhere from 6 to 24 tons per hectare, where a hectare is 100 meters square per year. I'm going to assume that I could get 10, right, which is sort of on the low side of the achievable numbers here. And if I had a square of land that was almost 70 meters on a side, that would be enough to, with some regular effort on my part, grow enough bamboo that over 10 years I could sequester all that carbon that is the average emission. Now, of course, there's a lot of stuff in here that I wouldn't actually propose. I mean, I'm not trying to move to, let's see where these plantations are: the Philippines, Japan, Indonesia, India, Japan, Ethiopia, Taiwan, Mexico, Bolivia, China. I kind of sort of want to live where I want. And I wouldn't like to spend all my time farming bamboo, even though I bet that I could get it done sort of as like a hobby rather than, having to work 40 hours a week at it. These exercises are just to get an idea of how big the problem is and how big the solutions would have to be. So what do we really learn when we go through exercises like this? Well, okay, so the first thing we learn is about my ideology and my mindset, which maybe you disagree with, and I'd love to hear about it in the questions and comments afterwards. So I think that, if you want to solve a big problem like climate change, you have to have a way of spreading the effort that solution requires across everybody in the population, right? Because we're all going to be affected by it. So at some point, we either have to do something about it directly or do something for the people who are doing something about it directly. And in this process, science can help us understand how big the problem is and what would help, right? And then technology helps us add efficiency to the process of a solution. And then politics is there to, ideally, distribute that effort equitably and humanely so that people have a fair, a nice say in how these solutions are managed and how this stuff all gets done. Another thing that I hope you've picked up and are convinced is useful is that if someone, okay, normally when people say one of these big context-free numbers, they shout it at you. They might shout the word billion or shout the word trillion. Try to find something to scale that number by to make it make sense. For example, when people talk about deficits of some country, right? The Dutch deficit is going to be a lot smaller than the Chinese deficit. And that's because the Netherlands has 17 million people and China has, over 1 billion people. So deficits are bigger or smaller when you scale them by the population. And normally when you take a deficit and you scale it by the population, you wind up with some hundreds or maybe $1,000. And so you can begin to think about how serious an expense, a deficit is if it's spread across the population, or interest payments on government debt. Another thing to think about is who those interest payments are made to, right? Because if the entire population of some country has bonds, then, it doesn't really make sense to harp on about how much interest the government is paying out on its debt because they're paying it to the population of the country, right? So they just get, money. That's fine. But the quantitative thing to do here is to take those numbers, right? People will talk about how expensive a bike lane is, but if you divide by the population of the city that's installing the bike lane, you could wind up with pennies. So find some factor to scale the number by to make it make sense. Of course, read this book, Sustainable Energy Without the Hot Air by David Mackay. And importantly, please don't act like anything I've said here is, the gospel truth. This has been a very rough exercise. I haven't taken into account ongoing emissions, right, which are a very serious problem, and those have to get cut. It's probably way cheaper and more efficient to cut those emissions than it is to start farming bamboo or crushing up rocks or whatever other carbon removal proposals are on the table. I certainly haven't taken into account what would happen, if everybody tried to get rid of their carbon contributions all at once, right? That Alibaba page that I showed you mentions in a spot that I didn't copy that factory only makes 200 tons of charcoal a month, right? So if more than 5 people ask for their carbon to be sequestered by that factory, right, their capacity is going to be strained. And of course, as a physicist, I like to think I know everything, or at least that I know a little bit about everything, but really, you should talk to an actual climate scientist about some of this stuff. And in case you're not convinced that I'm, an unserious person, you can see here that I've balanced my webcam on top of a trash can and roll of paper towel. So I think I'll close with that, actually. And if there are any questions about anything except for the roll of paper towel and the trash can, I would love to take them.
No, the paper towel and the trash can just show all of the innovation that you truly have. So thank you. That was really interesting. Would love to open the floor if anyone has any questions. You're welcome to unmute or raise your physical hand or Zoom hand, whatever's best. I see some unmutes. Mark, go ahead.
Ben, thank you. That was very interesting. Are you actually, you've used the climate change to illustrate a number of points. Well, could you tell us a little bit about are you working on climate change, or what problem are you working on?
No, well, this is just something that I can't stop thinking about. In my day job, I work on quantum computing. So there's supposed to be, well, okay. And the popular press about quantum computing is famously exuberant and frothy. There are people talking about how quantum computers are going to fix climate change. And then, later on in the article, they'll say that models that can, or I should say models of quantum computer, right, iterations of the devices that can solve relevant problems are a decade or more away. Well, if you want to get climate change licked, you should at least start doing something today, even if that something is really low tech and scalable, like charring wood into charcoal, right? It's not, it's not very whiz bang and it's not very technological, but you start out with carbon dioxide in the atmosphere and you end up with carbon in your hand. So that, that fits the bill. Happy with that, as they say in the UK. But yeah, so most of the time I work on fault tolerance in quantum computing. The idea is that, we're trying to use atoms or superconducting circuits or these other really intricate, delicate phenomena to process information. And error rates, while they've been coming down over the decades of development, are still pretty high. So usually when you try and do some quantum operation, you're off by about 1 part in 1,000, which is 1,000 parts per million. And so we have to design algorithms in order to effectively simulate computers that function well using larger computers that function poorly, right? To include redundancy in every message that we send, or every bit that we store in memory, or every operation that we perform, so that, in the end, you can infer what the answer would have been had you used a more reliable device. But yeah, nothing to do with climate change. As I said, I am definitely out of my field. If you're interested to know more, ask somebody better qualified.
that book you mentioned, Ben, sustainability, something about hot air. There it is.
Yep.
Without the hot air.
air.
Sorry, my bad. You know, it's available as a 10-page summary download. If you just want the quick version on the internet, you can easily access a PDF of the whole book as well. So it's very accessible.
Yep, and it's Cambridge University Press, which is still a reputable publishing house. And I'm not just saying that because they'll hear me.
I read an article, I guess it's been making, if I saw it, it means it's, you know, well out of the science world, like long time out of the science world, about seagrass being a wonderful place that's processing carbon for us. Seen it? Not seen it?
So there are a wide variety of proposals for how to fix carbon. Some people are into fertilizing the ocean with you know, small iron filings, or like chelated iron. And the idea there is that there are microorganisms that, you know, require iron as a micronutrient, right? And they're iron limited in their growth. So if you go dump a bunch of chelated iron in the ocean, what's supposed to happen is that these microorganisms will eat it and reproduce. And for every iron atom that they contain like 10,000 carbon atoms. So you wouldn't have to dump that much iron in order to fix that much carbon. But processes that rely on unseen deep ocean biology are sort of easy to misquantify or fib about. And so I prefer the woody approach, where you can see the stuff growing. You can actually hear it growing. It grows so quickly that it like makes popping sounds.
Bamboo?
Yeah. But that's just me trying to compromise between, you know, visibility and understandability, and maybe getting to do something with the output, right? People make bamboo furniture, paper, you know, whatever other useful product you can get from bamboo. You just got to make sure that it doesn't wind up as carbon dioxide by the end. Yeah, so let's see. Kelp definitely fixes carbon. Anything that grows, right, that photosynthesizes is going to fix carbon. And probably you would wind up doing a little bit of everything, because everything's going to have its own niche, right? You know, you'll notice that all of those bamboo farms were sort of close to the equator. So there's, you know, we would have to do different stuff up in Canada or here in the UK in order to play our part. But yeah, it's just there as a single sort of understandable example of how you might think about a solution.
Janice, the floor is all yours. And then I believe Lorraine turned her camera on. If you have a question, you're welcome to go.
Right. So is basically what we're trying to do is put the dead dinosaurs back in the ground.
Well, so we want to do a much more efficient process than waiting for dinosaurs to come back and then die and then go back in the ground. So we're trying to, yeah, I mean, basically what we've done is take an existing cycle, right? The carbon cycle, which is an ecological process where carbon gets fixed from the atmosphere, turned into plant matter, and then forest fires happen, it goes back up, right? Or it gets eaten by animals, exhaled, and then goes back up, or the animals die, decompose, and then it goes back up. That cycle has sort of exits. So for example, volcanic minerals like olivine will react with carbon dioxide in the atmosphere to form carbonates that tend not to be released again through some ecological process, right? So that carbon gets fixed. Also, if some unfortunate plant or animal gets buried as it passes away, then, you know, its carbon is trapped underground and doesn't get the opportunity to react with oxygen in order to become carbon dioxide again. So we've sort of taken that cycle and massively amplified the amount of carbon that goes up into the atmosphere, right? So there's a cycle, and we've sort of inflated part of that cycle. And if we want to keep the composition of the atmosphere the same, then we should inflate the other part as well, right? And probably not deflate a little bit the part of the cycle that we've inflated, right? So that we can get into an overall regime of carbon fixing for a bit. And then once we're at a concentration we like, we can rebalance everything. So we are trying to put carbon back in the ground or into minerals, but we're probably not trying to do carbon sequestration and storage, which is where people think they're going to pump liquid carbon dioxide into geological formations. You know, I think that kind of stuff is a bit dangerous because, you know, it's a big pressurized, naturally existing bottle of carbon dioxide, you know, and the pressurized gas or fluid is always going to want out. And it's probably just a matter of time before it gets out.
It's interesting that you ended on that particular note, because that was sort of along the lines that I wanted to, I guess, comment, is that in Canada, right now, one of the issues is around opening up the mining around what they call the Ring of Fire for the lithium and other things that are needed for batteries for electric cars, which are supposed to, you know, save the world. But the problem is that they're in areas of peat bog, which are big carbon sequestration fields, and, you know, are it's like a damned if you do and damned if you don't. Like, if you start opening that up, are you creating a bigger problem than you already have, you know, going on right now? So it's, I think we're at a very, like, a tipping point in time about, you know, as you say, is the technology there or is the science there to let us know what is the right choice to be making at this time?
Yeah, it is certainly extremely difficult to try to navigate the landscape of information and people who provide it to determine who's got what interests, whether what they're saying is driven by those interests or whether it's driven by facts. And it's been horrendously difficult for me and everybody else that I talk to try to figure out what are the actual ways that we can proceed. And of course, a lot of that is by design, right? There are, you know, there are plenty of environmental institutes for environmental policy that are funded by the Shell oil company. You gotta wonder whether that influences some of their conclusions, and whether all of this talk about natural gas as a bridge fuel, you know, is really being driven by unbiased, hard-nosed scientific inquiry, or whether there's a little bit of payola in the mix.
Exactly. Yeah.
Especially considering that methane, which most natural gas is like, you know, mostly made up of, methane is a much more powerful greenhouse gas than carbon dioxide. So, you know, if there's a leak from some pipeline, which I know it's needlessly alarmist to imagine that there would ever be a leak from a pipeline, but if it were to happen, then, you know, you'd have a problem that's thousands of times greater than if you were to flare the gas and emit the carbon dioxide, which is why you often see methane being flared, right? Which seems, you know, really wasteful and, you know, bad for the environment, and it is. It's just not worse than the immediate alternative.
Thank you, Ben.
Ben, can I come back to you again?
Sure thing.
Are you actually working with quantum computers? My understanding is there's not very many of them around the world. I had the fortune of seeing the one at IBM in the States, but is that one of the reasons why you globetrot?
Yeah, that's one of the reasons. So my PhD, all right. before you walk away with the impression that people who get PhDs are smart, I have an extremely specialized education. I wasn't thinking about this when I got the thing, but at any time globally, there are maybe 5 to 10 jobs open in the thing that I do. So when you want to move, you got to sort of pick a country off the globe and then go there. Maybe eventually one day it will be Canada, who knows? But for now it's the UK. And I am not in too bad a spot. The basic operations that we have now in our freshly merged company, Quantinuum, are I'm fairly certain they're the best in the world. I think they're the best published numbers in the world in terms of the accuracy of individual operations. We're almost at the point where we can make error correction work, where the error rates aren't too high so that the complexity that you add in error correction actually makes the problem worse rather than better. We think that some of the algorithms that we've devised, might actually function in real life. So we're all extremely gung-ho.
So Ben, you might want to share with the audience maybe what temperature you have to cool a computer down to make it work. It's like unbelievable.
Well, that depends on the computer, Mark. So the IBM quantum computers they use superconducting qubits.
Right.
And you might think, I've seen a superconductor where some kid from the university got a bunch of liquid nitrogen, poured it out in a beer cooler, and then this magnet was hovering above a superconductor. And that's legitimate superconductivity, but those superconductors don't work very well for qubits, even though qubits are the fundamental building blocks of a quantum computer, I should say. So let's see, and why not? Well, I'm pretty sure, well, okay. The problem that I'm definitely sure exists is that, one, it's hard to form wires out of those superconductors because they're ceramics, right? They're brittle materials. You can't stretch them into a wire very easily. It's not to say that it's like completely impossible, but nobody does it as of yet. There might be a couple papers on it somewhere. Now, what is the other problem? Oh yeah, even if you get the material to superconduct, thermal fluctuations can still add oodles of noise to any process that you would try and do. So IBM and other companies and universities, they usually go down to 0.02 degrees above absolute zero. And so when absolute zero is a temperature you can't get lower than, so we start to multiply temperatures rather than add them, right? In Canada, you'd say, 0 degrees Celsius, that's cold. -20, that's really cold, right? But we talk about 0.02 versus 0.002, right? Or 20 millikelvin versus 2 millikelvin. And then we sort of divide temperature by 10 as we get closer and closer to absolute zero, right? So that's really rough. In order to achieve those temperatures, they have a refrigerator that, instead of compressing and expanding some gas in order to absorb and release heat energy, what they do is they mix and unmix different isotopes of liquid helium. And that the phase separation and mixing occur at different temperatures. So you can have, the mixed high entropy phase in one part of the refrigerator and the unmixed low entropy part in another, and carry a little bit of heat energy between different bits. But the amount of cooling power is really low, and it only works at really low temperatures anyway. So what they do is they take that refrigerator and put it inside another refrigerator, and then they take that pair of refrigerators and wrap it in another refrigerator, and eventually you wind up with what you see on in the IBM press releases, which is a tiny quantum computing device attached to a brass stage, which is attached to another brass stage, and you keep going up. And each one of those, big sort of golden plates is the lid to a thermos, right? So that when you stick the whole thing in a giant can, each one of them mates with a vacuum separated barrier that insulates each stage of the refrigerator from the outside world. Why did I tell you all this? Turns out it was for no reason, because our quantum computers don't work that way. we do not use superconducting circuits in order to store information. We use trapped ions. And so, well, okay, this is being recorded, but I'll say it anyway. I like to tell people that this is proper future technology, because not only do the ions blink, right? They emit visible light, so they'll emit a small burst of light when you control them correctly, but also they hover above the surface of a microchip. They do not touch the chip. They're in the vacuum. And so in order to cool them down, you don't need to apply a lot of power because you're only trying to cool one atom at a time, right? In order to cool a microchip, there's tons of atoms in there, right? So you need lots of power, but in order to cool these individual trapped ions, mostly you make sure that the electric fields that are buffeting them around are not so noisy, right? That the electrons are the electrodes are pretty cold, I should say. And that you can do with like liquid nitrogen temperatures. Some people don't even bother with that. And then to cool the ions down, you use a special arrangement of lasers that was devised in the 90s in order to bounce photons off of them such that each photon comes away with a bit more energy than it went in with, subtracting kinetic energy from the ion that would otherwise be jiggling around. And you can get rid of one photon's worth of jiggling at a time until you get down to around about 10% of a photon on average. So 1 out of every 10 of these ions would have 1 photon's worth of jiggle to it, if that makes any sense.
So, sorry, I don't know if we're going in any particular.
No, go ahead, Laura.
So, hi Ben, I miss
Laura,
doing
how's it
improv with you.
Yeah.
Long time ago now. For the total newbie to your field of employment, when everything gets corrected, when we have all the bits needed to make it function properly, what could quantum computing do for us? Like, what would I, as the average person, see in the world that we don't have now?
That's a great question. And it's very difficult for me to give an answer that, doesn't come off like a pitch, right? Or that I'm also confident in. It's extremely difficult, I think, for anybody to predict the effect technologies will have. But I can say that right now, more or less half of the time spent on supercomputers, commercially and academically, is spent modeling quantum physics problems, either in material science for things, well, okay, without getting too pitchy, there are processes in our daily lives that rely on quantum mechanics in order to be described and designed, right? Solar panels is a big one, right? Existing solar panels are around 20% efficient. So of the light that falls on them, you get about 1/5 of the energy out of it. And if you wanted to get that number up, maybe a computer that can simulate quantum physics phenomena better would be applicable, right? There seems to be a pretty strong case to make in that particular area. Let's see, what else relies on quantum physics? So, I mean, of course, the design and maintenance of traditional computers as well as quantum computers also relies on quantum mechanics. And it's something that I, as a giant nerd, care about, right? I would love to have better computers, and especially better quantum computers. But that's sort of like circular reasoning, the idea that someone would care about quantum computers because you can make a better quantum computer with one is not as good a sell. So yeah, solar panels probably. That could be like a killer app. I mean, there are other materials issues as well. I like to say, maybe nanotechnology requires a solid quantum computer in order to do like computer-aided design. So if we wanted to get into some of that territory that's been discussed by Eric Drexler, where you would have these pseudo miraculous technologies that are available when you start manipulating or start making machines that are atomically precise or really small. That could be another solid area of application. Let's see. Yeah, there are others, mostly in chemistry, and chemistry is a pretty big field, right? And there are a lot of problems with chemistry as well today that are driven by our inability to do chemistry really well, right? So there are plants that photosynthesize all of these wonderful materials, right? Cellulose, medicines, all kinds of fantastic chemicals that are made naturally with almost no pollution. And whenever we try and make a chemical, there's always like just heaps of unwanted, even from like a really, even if I was one of the Captain Planet villains, right, who run these huge companies, allegedly, then I would still view it as an expense to create and then have to dispose of all of this pollution, right? I've bought all of this feedstock from feedstock.com or wherever I get it, and then run it through some giant boiler or whatever, and now I've got a bunch of fluorinated garbage on my hands that I have to handle, and that's tremendously costly. So if we understood how chemistry occurs in nature, and how light in particular can become a part of chemical reactions, right? We might be able to do with a lot less pollution. And I mean, not only carbon dioxide, but also other, occasionally more impactful kinds of pollution. We might be able to do a broader array of things with atoms, right? To make molecules that we care about. So those are roughly the areas where we think quantum computers will be applied. But for a technology this general, probably people will look back in 20 or 30 years and have a good chuckle at what I thought quantum computers would be used for. Everyone will be laughing except me, of course. I'll just be thinking about how much hair I used to have.
Paula, and then back to Mark.
Okay, but what a great haircut you have with that hair.
Many thanks to the United Kingdom. God save the Queen. Yes. Happy Royal Jubilee.
The Jubilee haircut. I'm curious about what I like. You hear it called quantum communications, and China's, heavy research and satellites that do they not take that? What you're working with is related to that or not?
Oh, many of the same mathematical techniques get involved in quantum computing and quantum communication, and there are lots of researchers working on ways to get quantum computers to talk to one another. Right. One of the disadvantages of working inside a fridge that's inside a fridge that's inside a fridge that's inside a fridge is it's very hard to get quantum signals out and into a form where or onto a carrier which will be stable at room temperature and pass through the air. And so there's a whole cottage industry or subfield dedicated to interfacing quantum computers and quantum communicators or quantum communications, so that we don't have to use one device for all of the quantum computing that we're going to do. Now let's see. Are there other things to say? Well, all right. Beware of what is called trusted quantum communication, because maybe it's defined to be trusted because no one would actually choose to trust it if they knew what was going on. The idea behind quantum communication, incidentally, is that you can use the inherent fragility of quantum states in order to make communication channels that are tamper evident. If anybody is eavesdropping, the idea is that quantum physics guarantees that measurements that they make on the signals that are being used for communication disturb those signals and leave an imprint that can be detected as evidence by the people doing the communicating. The math behind that is all pretty sound, but the engineering, you could run into hiccups, and there are people whose quantum communicating devices have been hacked in the wild, and then.
Interesting.
Oh yeah, well, they get fixed. You know, people take this stuff a little bit seriously. Which is
And
nice.
there's the competition amongst, you know, country to country must be very rife, I would think.
Well, yeah, I mean, as usual, the politicians are making a lot of hay about competition, and the scientists will phone each other up to ask for tips, and it's not a big deal for us. So, you know, I wish we could have a much saner international arrangement on all sides, and you know, just hit the books and get this thing done. But unfortunately, you know, there are people on every side of the ocean who have to interface with those politicians and work with them in order to achieve great things. We are still being recorded, right? Wonderful things they're achieving, amazing progress for humanity.
Okay.
Yeah, Mark, go ahead.
It's Hinda Levine.
Thank you.
And I just wanted to say hi to Ben. It's lovely to see you. I don't know if you remember, but I taught you in Tibet many years ago.
Oh, yes.
And I remember at the time from the questions that you were asking that it wouldn't be very long before you were out of my league. And it's so, you know, here you are asking questions and looking for answers way, way, way out of my league.
10
So,
10 to the 14th.
so congratulations, and you know, lots of luck to you. And again, it's lovely to see you.
Lovely to see you as well. I hope I've managed to demystify something at least, and that people, you know, not just you, but everybody feel more equipped and emboldened to pursue your own answers to some of these big questions that people often, you know, that people often use for obfuscatory purposes.
Great presentations always answer questions and leave you asking more. Does anyone have any last minute questions before we let Ben have his late afternoon, I suppose, back in the UK? How did you decide you wanted to do this?
Well, this talk or get into this field?
Get into this field.
Okay. Well, I mean, of course, like I could tell a self-aggrandizing story or a self-deprecating story, and either one would be true, right? There were a lot of steps along the path that led me to quantum computing. I mean, one of them is that in 2007, when I was taking undergrad courses in third year, they gave the first one on quantum computing at Mac. And I thought, oh, that seems easy. You know, the first time they teach a course, the prof doesn't know what they're doing. So they make it really easy so that nobody gets angry, right? I'll take that one. Little did I know it would become my job. I mean, and there's also, you know, how I got into quantum error correction and fault tolerance. I read a paper where the opening paragraph said, you know, there is absolutely no quantum computing without fault tolerance. And I thought, wow, if I work on that, then, you know, I've got my meal ticket. So, you know, there were a few, in retrospect, that was probably the good idea that I've had in my life, is to find that spot where it says in the paper, and this stuff gets past the reviewers, gets past the editors, gets past everybody signs off on it. Right? There is absolutely no way that we will have the benefits of quantum computing without some kind of fault tolerance. I thought, ooh, yeah, I think I'll work on that because it seems necessary. They got to pay you to do that, you know.
Perfect. That was a great way to end off, a little nod to the past. So thank you so much. It was so great to hear all about what you do and all the things to come. And I'm gonna turn it over to Cantor Paula.
Okay, so Rabbi Cohen, as you know, went out to the Temple Anshe Shalom Cemetery today to help a couple of families of ours to remember their loved ones with an unveiling of a memorial stone. And so he can't be here to say these words, and I get to do it in his place, and I'm grateful for that. So So Ben, you are the culminating speaker in our 5 series of this next generation. I feel like it was a genius idea. Oh wait, it was mine. Yeah, I'm doing my best Ben Criger imitation. It was a wonderful thing to have our young people come to the fore and get back in touch and feel in connection with all of the 5 that presented. It's been fascinating. I just feel like the future is in such great hands, and I have learned so much by all of the presentations, and you have blown my mind today. I didn't even know. Here's how, I'm not going to say old. Here's how uninformed I am, Ben. You know, I'm an artsy person, and so I didn't even know there were quantum computers and that they were different from other computers. And now I'm Googling, and I'm looking at that book, and that's good. You're moving people in the right direction. So I thank you for that. I thank you for that. I want to also, I'm going to shout out to Misha Appel. So the breath of fresh air that has really made this next generation so enjoyable has been to have this incredible law student, this brilliant person, this beautiful persona who's caring and thoughtful and has amazing questions to be our host for this series of 5 presentations. Misha, you have been incredible. I hope you will keep us in mind if we do this again next year. I hope we will do this again next spring. You've just been a wonderful face for Temple on Shalom. Thank you so much for that. Thank you to all of our regular Breakfast Club people. It's amazing. Great to see the Criger family out. So nice to see you. You know, it's been 2.5 years since really we've seen anyone's face in person. We're really looking forward to Shavuot next week and being in person again, and also gearing up now for high holidays, and that's going to be back in our temple sanctuary. So we're really excited about that. Ben, all the best in the UK. Wonderful summer, great things. So want to wish everyone all the best, and happy weekend. Shavua Tov, everyone.
Shavua Tov.
Thank you so much.
Shavua Tov.